Module 5 Investigation 1, The Bottle Problem, Modeling Relationships in a Context. 1. Examine the bottle given below and imagine the bottle filling with water. Make a possible rough sketch of a graph of the height of the water in the bottle as a function of the volume of the water in the bottle. Hint, it may be helpful to imagine adding equal amounts of volume of water and consider how the height of the water in the bottle will change. So we have on the horizontal axis volume of water, and on the vertical axis height of the water in the bottle. So I imagine if I put some water in here, let's say 1 unit of volume, maybe something like this. Then certainly my height is going to increase. So I could just call that increase the point right here. So now if I add the same amount of volume, I'm going to use a different color for it. Notice how this is, the bottle's skinnier. So if I try to put the same amount of volume that I put before, like the same thickness, notice that I don't have as much length to go across, so this volume is going to be a little bit higher. The distance from the top here to this bottom green part is higher than the distance from the bottom of the blue part to the top of the blue part. So this next point, I'm going to increase a little bit more. So when I go one more unit of volume, I'm not going to be exactly the same change in height from 0 to this point here, but there's a little bit more. And then if I fill in the same amount of volume again, it's going to go even higher because I don't have as much length, so I have to compensate and make it thicker or higher. So if I go one more unit of volume, then I'm going to have to go up a whole unit and a little bit more, and then even a little bit more than I did before. And so we're going to keep doing this. If I try to add the same amount of volume, then this is going to just get thicker than it was before because I don't have as much length. So my height's going to, this change in height's going to be larger. So go up 1 unit, but it needs to be a little bit more, a little bit more, a little bit more, something like right there. Let me just try maybe 1 or 2 more. So then if I add some more volume, the same amount, I'm going to have a pretty big change in height here. Notice the change in height is increasing for each of these units of volume that I add. So this change in height, for 1 unit increase in volume, maybe something like here. So notice that each of these changes in heights has increased. And I basically have an increasing function but it's getting steeper and steeper. So the rate of change is increasing as well. Notice if I add like 1 more unit here, This is going to be kind of strange, but I think it's still just going to keep going up. So something like that. So is that all we need to do? Make a possible rough sketch of the graph. So the important thing to notice here is that, for one, as the volume increases, the height increases, but more importantly, as the volume increases, the change in height increases. This isn't a constant function. It's more like an exponential growth function, but I'm not sure if it's exponential or not, because we don't know if there's a constant growth or constant growth rate. Number two, using the bottle animation. Imagine filling the bottle with water and complete the following table. Create a revised sketch of the graph of the height of the bottle, water in the bottle as a function of the volume of the water in the bottle. So, I am not able to access this. I'm not sure how you are supposed to be able to access it. But I'm going to go ahead and fill in the table, and then we'll look at a graph. So I have the answer key, so I know this is what the bottle animation would tell us. Maybe that bottle animation link is in the online textbook. I didn't see it. I thought it might be in the instructor's PowerPoints, but it probably is, but I couldn't access it because of some Java security issue or something that I tried to resolve, but I couldn't. So let's assume this is what the data we get, the volume of water and the height of the water, and let's go ahead and graph this data. So if the volume of water is 0, the height is 0, so we know this point 0, 0 is part of our graph. When the volume is 1, the height is 0.5. When the volume is 2, the height is 1 1/4. When the volume is 3, the height is 2 1/2. When the volume is 4, the height is also 4. When the volume is 4.25, the height is 4.4. When the volume is 4.5, the height is 4.8. That's all we got. So we see some sort of graph like so. Again, it looks exponential. What does your graph convey about the height of the water in the bottle and the volume of the water in the bottle change together? Or about how the height of the water in the bottle and the volume of the water in the bottle change together. Be sure to explain how the amounts of increase in the volume and amounts of increase in the volume change together both before and after the neck of the bottle. So I'm sure that should be height and volume. So as the volume of water increases, the height of the water, or height of the water in the bottle increases. That's pretty obvious. Also, be sure to explain how the amounts of increase in the volume and the amounts of increase in the height change together, both before and after the neck of the bottle. So I'm not sure exactly what this means, but as the as the volume increases, the change in height also increases. So just notice that we can see this on the graph. Like if we look at this change in volume here, there's a pretty small change in height. But if we look at this same change in volume, the change in height is much bigger. this change in height is about half a unit, and this one is about 2 units. So as the volume increases, those changes in height are also increasing. I just thought about something. Even though that neck was pretty small, the change in height would be constant at that point. It's hard to tell since we were adding such a large amount of volume here, but if we added the same amount of volume for each of these increases, then we'd have a constant increase in height at that point. Let's see. Calculate the following average rates of change of the height of the water with respect to the volume of the water and explain what these values mean in the context of the problem. Okay, the average rate of change as the volume of the water increases from 1 to 2. So from 1 to 2, the change in volume is 1, and the change in height is 1.25 minus 0.5, which is 0.75. So that means that the change in height over the change in volume is 0.75 over 1, or 0.75. Explain what this value means. Let's see. I'm pretty tired tonight, just trying to keep up with the class. 2 investigations per class is a lot. You guys are doing good. 0.75 units of height per unit of volume is the constant rate of change required to achieve the same change in height, 0.75 units, in the same change in volume. Another way to think about it is it would be the slope that connects these 2 points here of a straight line. Because we had we didn't have a constant rate of change here, but the average rate of change is the constant rate of change needed to achieve the same change in height for that 1 unit change in volume. Next, we're asked to find the average rate of change as the volume of the water increases from 2 to 3. So from 2 to 3 here. Again, the change in volume is 1, and the change in the height is 1.25. So the average rate of change is 1.25, delta H over delta V. 1.25 over 1. So the interpretation is the same. 1.25 units of height per unit of volume is the constant rate of change required to achieve the same change in height, which in this case is 1.25 units, in the same change of volume of 1 unit. Okay, and then the average rate of change as the volume of the water increases from 3 to 4. Again, we have a change in volume of 1 and a change in height of looks like 1.5. So this means 1.5 units of height per unit of volume is the constant rate of change required to achieve the same change in height, which was 1.5 units, in the same change of volume, 1 unit. What's interesting here is that the rate of change is increasing. Notice it's not increasing at a constant by a constant amount, because this difference is different from this one, but the rate of change is increasing as the volume increases. And that's what we notice here. 3a, use the graph of the function f that represents the height of water in the bottle in terms of the volume of the water in the bottle to complete the following table. Okay, we got volume of water in terms of the number of cups, height of the water in centimeters. So when the volume is 0, the height is also 0. When the volume is 1, the height is, I don't know what that is, about 12.5. Let's see, when the volume is 2, the height is about 17.5, or maybe a little bit less, maybe 17. Let's see, when it's 3, we have 20. When it's 4, 22. I'm going to go ahead and just fill out the rest of these. Let's see, now we want the average rate of change of height with respect to volume. Now, the average rate of change is simply the change in the output, or change in height, over the change in input, change in volume. Notice that each one of these volume increases is 1 for each of these sections, so this is always 1. And so in this case, the change in height over change in volume is simply equal to the change in the height. So here the average rate of change is 12.5 because the change in height is 12.5. Here this change is 17 minus 12.5, which is 4.5. This one is 3, 2, 1, then 2, 3, 4, 7. Okay, so this is really cool. Notice the pattern here. We have a pretty large average rate of change, then it decreases, then it starts increasing. And we can see that on the graph looking at the steepness. First we have a pretty steep graph, so that corresponds to a pretty large average rate of change, but then it starts to become less steep, so the average rate of change decreases till we get to about 4 to 5. The average rate of change is 1. So we level off here, but then we start to increase again. The average rate of change increases. That's pretty cool. This point here, around 4 or 5, somewhere in here, and this is called an inflection point because the graph changes concavity at that point. We go from this interval from about 1 to 4, where the average rate of change is decreasing, and then the average rate of change starts to increase after that point. The graph slowly becomes less steep, and then it gets steeper and steeper and steeper. Use the graph of f and table of values for f to answer the following questions. On what interval of the function f is the average rate of change decreasing? Okay, so to me, it looks like it's from about 0 to 4, and then we start to increase again. The book says as the volume increases from 0 cups to 5 cups, the average rate of change are decreasing because for equal changes in the volume, the corresponding changes in height are decreasing. I'm not sure how they decided on 5 or 4 because we don't I think you could go either way there. Okay, so the average rate of change is decreasing on this is the input interval from about 0 cups to 4 or 5 cups. So during this input interval here, the average rate of change is decreasing. The slope of a tangent line to any point on this graph is getting smaller and smaller and smaller. But then around this point, the slope starts to increase again. The curve begins to get steeper. What predictions can you make about the shape of the bottle on this interval? Let's see, so the changes in height are getting smaller and smaller and smaller. To me, that would mean something like we start with our bottle, and then it's going to get wider because this length must be getting greater if the changes in height are going to get smaller. Let's see, the book says on this interval the shape of the bottle will get wider because for equal incremental changes in the volume, the change in the height is decreasing. This makes sense because as the bottle is getting wider, the height will not change as much for equal increases in volume. So we expect the bottle to get wider from the base to the top or just from the base, I should just say going up or something like that. Because then I think that it's going to change, and we might want to give a reason, because as the change in volume is constant, the change in height is decreasing. So that's why we know it's getting wider. But then what happens next is that it's probably going to get skinnier because now these changes in height are increasing. Describe how the changes in the average rate of change of f on an interval relate to the shape of the graph of f on intervals of the function's domain. Hint, when the average rate of change of the height with respect to the volume is increasing, decreasing on interval. So, relate to the shape of the graph. To me, when the average rate of change is decreasing, your steepness starts to decrease, but when it's increasing, your steepness starts to increase. Let's see what the book's answer is. The purpose of this question is to introduce the idea of concavity relative to increasing and decreasing rates of change. It is possible that this is the first time students will be exposed to the term concavity. When the average rate of change of the height with respect to volume is decreasing from 0 cups to 5 cups, the graph is concave down. When the average rate of change of the height with respect to volume is increasing from 5 cups to 9 cups, the graph is concave up. Okay, so there's some terminology you guys aren't familiar with yet, but we say that if the graph of a function looks like this, that's not very good. That's not going to work. That's pretty close to what we call concave down. And if the graph looks like so, we say it's concave up. Now, here the steepness decreases. it decreases as we get to this point. Now here we say the steepness is 0, and then the steepness is negative. You can think about this as the slope, or the average rate of change, even the instantaneous rate of change if you've had calculus. The steepness gets smaller and smaller and smaller, then it's 0, then it becomes negative, but it gets larger, more negative. But here, with concave up, here our steepness is negative, our slope is negative, it becomes 0, then we increase. So for concave up, the rate of change is increasing, and for concave down, the rate of change is decreasing. So when the average rate of change of the height with respect to volume is increasing, the graph, let's see, is getting steeper, and this is concave up, and that happens from the interval about 4 to, I don't know how far this graph goes up, from about 4 to 9, where concave up, we're increasing. And when the average rate of change of the height with respect to volume is decreasing on the interval, like from 0 to 4, we say that's concave down. Notice that concave down shape here, and the concave up shape here. And so that's becoming less steep. Sorry about the misspelling there. There's another E. Okay, number 4, part 4. Draw a picture of a bottle that would produce the volume-height relationship conveyed in the table and graph of F. So we started doing this. We had our bottle, it gets wider, but then it's going to start to get skinnier. It's not a very good drawing. Let's see, what else does it say here? Label landmarks on your bottle and the graph in part A, where the rate of change of the height with respect to volume changes from either increasing to decreasing. So I hope you guys are better artists than me. Really need this three-dimensional, but right here in the center, where we stop becoming wider and we start getting skinnier again, that's where we're going to see this change in the graph, right about this point where the rates of change start to increase again, meaning the heights are going to be increasing if we increase the same amounts of volume. So, hope you guys are reading the online textbook. Good luck.